right, so first LP spaces with the curly version. So what's that? So for now, I skipped the parentheses here. You can put where you specify exactly which space you're on and so on. So it's functions of whatever x, sigma, algebra, and mu, such that the following norm, which I'm now introducing, is finite. Now, of course, I just said norm. We agree that this is not a norm. So to deal with that problem, let's call this now. So it has the properties of a norm, except for the fact, for the one that this is zero if and only if the function is zero. It usually doesn't have that. So to have a terminology for this still, we call it a semi-norm. So a semi-norm is something that acts like a norm, but doesn't have that one property. Okay, so you see, what did I do? I put a p. If p is equal to 1, I get the L1 space, yeah? So this is fine. And then previously up on my example, I also had L2, which we got from like just generalizing the scalar product. And let's recall, how was that? You see? The L2 space comes out by choosing p equals to 2, then we get this guy here. Okay, so this L2 space is particularly nice. It's a Banach space, but when the norm comes from a scalar product, which has its own definition, I'm not going into it. Well, okay, it's linear in the first and anti-linear in the second. If anti-linear, well, complex linear. Okay, if we're in a complex space. Otherwise, it's just linear in both. And also with the property that scalar product with itself is zero if and only if f is zero and so on. Okay, so for anytime you have a scalar product, you get a norm or semi-norm. Okay. But if you have a semi-norm or a norm, it doesn't necessarily come from a scalar product. In fact, the only of these guys which is comes from a scalar product is when p is equal to 2. So, and that's unfortunate because the scalar product allows us to talk about angles, right? Allows us to visualize things like angles. We don't have this in this generality. And actually, we don't even know yet if this is a norm because we have to prove stuff like the properties of a norm, right? The difficult one being the triangle inequality. You know, if I put an alpha here, alpha goes here, it pops out, it gets a p on it, and the modulus goes out of the integral, and then the 1 over p goes on it and annihilates the p, and then it's just modulus alpha on the outside. So that one is immediate. Okay. What do I write here? First of all, 1, p should be less than, for now, it should be strictly less than infinity. We're coming to what happens. I'm allowed to put infinity also, but then I have to change the definition a bit. So we ignore that for now. Okay, so the following property is more or less immediate. That is non-negative is also immediate, and then okay, but the triangle inequality, how? I mean, then that becomes difficult, right? And I would have to deal with f plus g. I put an f plus g here to the power of p. Now, if p is 15, what do I do with that f plus g to the power of 15 or 14 and a half? Are you going to start like expanding it 14 times, and then, you know, it's not clear at all how to deal with that. In fact, if you haven't never seen Hilbert space theory, you might even not even know why this is satisfies the triangle inequality. So let me prove you that. There's a very nice short argument for that based on the Cauchy-Schwarz inequality. So anytime you have something that behaves like this, go back to your vector space or linear algebra, whatever textbook, and look at the proof for the Cauchy-Schwarz inequality, because it works verbatim or whatever, you know, exactly the same in this more abstract setting. So what we do have is Cauchy-Schwarz. the Russians like to add Minkowski also, because everything that somebody did in Western Europe, they claim that they did it before and put some Russian name on it. But we don't do that here. We just say Cauchy-Schwarz. All right. Now, okay, the inequality looks like this. So, armed with this, we can now start to think about the triangle inequality. Okay, I'm adding a 2 here, since we can deal with different norms. So what is this? Well, here I have the luxury of having an alternative definition, right? So it's the scalar product of f plus g with itself, and then with the square root. But now, okay, so I can expand this. It's linear in the first one, and then I use also that it's linear in the second. So what I'm getting is f comma f plus f comma g plus g comma f plus g comma g. Yeah, this doesn't look very nice, but aha, that's the other thing I forgot. All right, so the scalar product should also have this property that if you, in the real case, if you flip the order here of f and g, it doesn't change. Yeah, if it's complex, then you have to worry with some complex conjugate. We're not dealing with that now. So this, I can write 2 times f comma g, but then f comma g is less than or equal to this, right? So altogether, here I get this guy is just norm f squared. Then I have 2 norm f norm g plus norm g squared. Okay, that doesn't look very nice, but if you look at this from a sober perspective, you see that, you know, once you do a plus b squared, you know the formula for that, right? A plus 2ab plus b squared. And then you realize that, aha, that's exactly what's going on here. It's just that a is going to be my norm f, b is going to be my norm g. And then, well, so this is this, norm f plus norm g squared, and then a square root. Well, that disappears, right? So then what I get left here is this. Okay, so that was a very short argument leading up to the triangle inequality. So then we say, oh, okay, let's do something similar here with the LP spaces. Unfortunately, that's not going to be so easy. But that's the path we're going to choose. We just need to figure out what to do, replace this the scalar product and Cauchy-Schwarz inequality with, because we don't have a scalar product here. There's no scalar product. You could still start thinking about, all right, something like, I mean, what would be, so this thing here, that would be the norm, f times g multiplied, and then just integrated with the modulus outside here. So the most natural thing to guess would be this inequality, right? Replace like that. But this is false. So an example of that, just let u be equal to lambda, x be equal to the interval from 0 to 1, and the function f equals to g equal to characteristic function 0 to 1. Okay, with open times 1 over square root x. So this is some function that, goes to infinity like this. So what's going on with this guy? Well, if p, let's say just p equals to 1, then I can integrate that, right? This is just, anytime we have functions that are Riemann integrable and we work with the Lebesgue measure, we use our own formulas. So here the primitive is like square root of x with some 2 somewhere. But anyway, that when you evaluate that, you get a finite number. So in fact, if p is any number less than 2, this is in that LP space. It's interesting, when p becomes equal to 2, it's no longer in the LP space. So these LP spaces are really different. This norm can be finite for some values of p given a certain f, and then be infinite for other values of p. Point here is that if p is equal to 1, then this number is finite and that is finite. But once I multiply these two, I get 1 over x, and the integral of that is infinite. So it's not that we have It's not a problem that we don't have the inequality. It's worse than that. The left-hand side doesn't even exist. So given one of these LP spaces, how can I even, it's nice to multiply two functions and integrate them. We saw here an application of it. So what sort of, given an LP, say f is an LP, what function g can I put there so that I even get a finite number in my integral? Turns out there's a magical choice. And this is beautiful. Someone thought a lot, came up with it. I don't know who, it doesn't have a name attached to it. But there's something called conjugate exponent. So for every p, there is a q, such that if he's in LP and he's in LQ, then this number over there is finite. And there is some sort of magic going on there, right? So you're going to see it many times. You go like, there's like lots of p's and q's, and they all disappear at the end of your calculation. You go like, what happened? Sorry, I can't tell you what happened because it's just clever. Right, so here's this magical choice, conjugate exponents. So given p, now let's take them between 1 and infinity, so not equal to 1. Its conjugate exponent is defined by, I'm going to write up a formula, 1 over p plus 1 over q equals to 1. So in particular, if p is equal to 2, then q is also equal to 2 because 1/2 plus 1/2 is equal to 1. For all the other values of p, that doesn't happen. And also, what's with the 1 and with the infinity? Okay, to make this lecture like within reasonable time frame, the extreme point when p is equal to 1 is always easier to deal with than the other values of p. So I'm just going to ignore that in the lecture, but I'm telling you now, anytime p is 1, then I have 1 plus something is equal to 1, well then q is going to be infinity. And things are always going to work out with this pair also. One is 1 and the other one is infinity. But then we need to define this guy, what's called the L infinity space. I'm probably going to write out the definition at some point, but it's basically the supremum norm. But you kind of ignore some sets of measures here. So yeah, but mainly I focus my attention on this thing here, and the book does all the cases. So we're going to talk about this case because it's the most interesting and difficult one. So okay, it's good to have some formulas, some other ways of introducing these guys in mind so that you recognize them when they show up. Now I wrote all over the blackboard, but anyways, let me pedagogically make a green box here, right? So you can't see it. Okay, like this. So this is useful formulas. So if I multiply both sides with p and q, I get pq equals to p plus q. That's one identity. And then you can express q as a function of p by solving this, and you get p divided by p minus 1. Okay? Just try to look at them and memorize them, so then it's easier when you see them that I'm just going to flip it around and say, okay, this becomes a q, or this I can replace it with that. The good thing is p, I said p is between 1 and infinity. What about q? Well, it's also going to be between 1 and infinity, right? Because here I'm going to get a number between 0 and 1. So this number also has to be between 0 and 1, meaning that q has to be bigger than 1. And of course, less than infinity. So the two key inequalities, which is the core of today's lecture, this is section 3.3 now, is called Hölder's inequality and Minkowski's inequality. Minkowski's inequality is just a triangle inequality. It's called that when you are in integrable, in function spaces, LP spaces. Okay, so key inequalities. If f is in LP and g is in LQ, then f times g is in L1. And here comes the key point. If I integrate now, putting the modulus on the inside, you could put it on the outside, but this way it becomes even stronger. The mu, it is less than or equal to f, the p norm of f times the q norm of g. Yeah? So, of course, we know that I can move the modulus on the outside. If I do that, and I let p be equal to 2, then q becomes equal to 2, and what's written here is just the Cauchy-Schwarz inequality. So this is like, even for p equals to 2, it's a bit of an improvement of the Cauchy-Schwarz inequality because I put the modulus on the inside of the integral. But much more than that, it is what we were lacking in the previous example. It's a way to make the product of two functions always be in L1. So this integral exists. And moreover, we have this nice estimate here with no silly coefficient here that we have to remember. It's just the coefficient is 1, so to speak. Minkowski. Just a triangle inequality. Also, Hölder is called Hölder's inequality. I was a bit lazy. So this finally then proves that these LP spaces with the curly thing are semi-normed spaces. Yeah, we still lack this property that if the norm is 0, then the function is 0 most of the time. Not that the function is 0 most of the time. For most mu's, we lack this. For some mu's, we have it, but for most of them, we don't have this. So for Lebesgue measure, we don't have this. Okay, and now we get into some really beautiful mathematics of how we're going to use Hölder. Even to prove Hölder is a nice trick, and then how we get to Minkowski is it's also very beautiful. So there is a basic underlying identity here, which just takes this down to analysis 1. So we prove Hölder first, and then Minkowski. Okay, so if x and y are non-negative numbers, then the product is less than x to the power of p divided by p plus y to the power of q divided by q. There are many different proofs of this, and the book has one. It's 3.3.1. It's boring. Exercise 3.3.2 gives a beautiful geometric proof where you can really visualize this. And I'm just going to paint it. So you consider some sort of curve here, and then you interpret this thing. So you have some y here, some x here, and then you interpret one of these numbers as this area, the other number as that area. But then you realize that x times, oh, sorry, this should be x times y is the area of the box, right? So this little piece here that overshoots gives you the inequality. Beautiful. I'll let you work that out yourselves. I'm going to give you a third option, which is I found somewhere else, based on the idea of convexity. Yeah. So the proof in the book is boring. It's just like there are so many different ways of proving same statements sometimes. You can do geometric. The proof in the book is more like analytical. You just consider derivatives and stuff of some functions you define. That's usually the boring way of proving things. And then you have this concept of convexity. Okay, so your convex function. I'm not going to go into that, but well, a convex function. Sorry, that was wrong. Okay, let me just mention, God damn it, I didn't want to do this. I have to put a half here and a half here as well. But, okay, what is a convex function? Well, if you have 2 points in a space, so you think about, this is just like x1 axis, x2 axis, and there might be more axes here in a higher dimensional space. But if you have 2 points in a vector space, you can always look at the line between them, right? So if this is x and this is y, then any number on the line between them can be written as alpha x plus beta y, where alpha plus beta is equal to 1, right? So that's taking an average. That's a nice exercise to figure out that all these combinations gives like a parameterization of this line. Okay, but then I can actually put so all these points here. I can also get to them by thinking of, you know, x divided by p plus y divided by q if I allow p and q to be floating points, right? So and what is convexity? Convexity is that anytime you have a point here in the line between, if there now is some function, you know, you think of it as sitting on top here, so you have some function values, then the value here of the function should be lower than the value you get by connecting, you know, the value over x and y by a straight line. So convexity says alpha x plus beta y is less than or equal to alpha phi of x plus beta phi of y. That's what convexity is for all alpha and betas, again, such that we have this. Okay, so armed with that, we know that e to the power of x is convex. So in other words, I mean, in a one-dimensional setting, convexity is very easy to paint, right? So this formula here, which I wrote, where is it? This one, if this is a function phi, it just says that, okay, you know, here's my x, here's my y. So if I take some average, you know, this point here, then what I have here, phi of ax plus beta y, or alpha x plus beta y, will be the value above this point, right? Whereas what you have on the right-hand side here is the value on the straight line between those points. It's also a nice exercise to work out. So this is convexity, so we can visualize it, right? It's something that's like this. And in particular, then e to the power of x is convex. Okay? So what can we do with this? Let's get our focus back. I want this inequality here. These x and y's over here are not going to be the same. Now, x and y are just real numbers, positive, no negative. Okay, so I set x, I'm going to write that as e to the power of s divided by p, and y I'm going to write it as e to the t divided by q. This is nice. Now look at this. So x times y is equal to e to the power of s divided by p plus t to the divided by q. Well, now I use this, that is 1 over p plus 1 over q equals 1. So I have this convexity property. So, you know, thinking of this as e to some exponent, which is this guy. And then put a parenthesis here if you want, so then you really see it. Now by convexity, this is less than 1 over p, e to the power of s, plus 1 over q, e to the power of t. Well, but e to the power of t, that's y to the power of q, right? Because if I raise to the power of q here, then this q disappears and I just have this left. So here I'm writing, yeah, short, elegant, very nice. Welcome to my papers. All right, so let's get on with this. The blackboard has dried while I've been on social media. Okay, so what did we have? We had, let me see, yes. we had this inequality, right? That's what we're armed with. Right, so I realized I messed up. We take it from the beginning. So what are we armed with here? We are armed with this inequality. And then a very natural thing to do is to take, we're interested in the integral of f of t times g of t modulus the mu. And then I can add like, all right, so this is the modulus of f of t times the modulus of g of t. Now I have two non-negative numbers. I apply this inequality, and what do I get? I get this integral of that thing, but then the integral is linear, right? So I can move in, just integrate him separately and that one separately. And then I have integral f to the power of p, but I don't have the parenthesis outside with the 1 divided by p, right? So I get here the p norm to the power of p divided by p. This comes from the first guy. And similarly here, I get the q norm of g divided by q. Okay, this is a true inequality. It's, the only problem is it's not the one we wanted. It's not a very interesting inequality. I've never used it for anything. What do we do? There's a very beautiful trick here to get around this issue that we didn't got the desired result. So instead, so the reason I use t is, of course, I don't want to use x as the independent variable as well. Okay, do capital F of t equals f of t divided with, I'm just rescaling, moving this a bit down or up depending on what's the norm of, or semi-norm of f. And then I do the same trick for g of big G. And now I do this computation again, right? So this multiplication here, well, okay, so let's do this. So f of t times g of t, the mu, is equal to integral f of t Okay, so now if I consider the integral of f of t times g of t, I'm getting tired. I'm getting this, which in turn is equal to integral. Right? I have this formula here. And so now what we see is that the inequality we're actually after is to say that this is smaller than or equal to this times this. Well, that's the same as proving that what I have here is less than or equal to 1. So then let's repeat this trick, but with big F and big G. Then I get, okay, so integral so I skip some steps. I go immediately over here. And what I get is okay, that looks a bit bad, but okay. So this looks a bit bad, but it's not. So if you just look at this guy without to the power of p, I have the norm of f divided with the norm of f. So here I get, this number can go on the outside, so 1 divided by this. And then I have norm of f divided by norm of f. At the end of the day to the power of p, but that's just 1 to the power of p. So here I get 1 divided by p plus 1 divided by q. And that is by the defining property of conjugate exponents equal to 1. Very short. Why does it work out, this argument? Well, I can't really tell you. Somebody, this is one of these shortcut proofs that there's probably some basic proof around, but this one is so much faster. Or this is the way to do it. I don't know, but I don't really see what's going on here. It's an elegant trick. That's what it is. Okay, so that was Hölder's inequality, right? This is less than or equal to 1. It means that this quotient here is less than or equal to 1. So this is less than or equal to this product, Hölder's inequality. Now, so there is something called duality, which we will do in the continuation of this course. So basically, we're looking for, when we have Banach spaces, it's so nice to have this scalar product in the Hilbert space. You know, you can take the scalar product of f and g and fiddle around with it. So we want something that replaces that in a Banach space. And it comes here. So with these conjugate exponents, I mean, this is like a scalar product, this integral of the multiplication. And it satisfies Hölder's inequality, which is some sort of a generalization then of Cauchy-Schwarz. So given a P, the corresponding LP space with a Q is going to be called a dual. And if you know a bit about duality theory, I'm going to show you the idea of how to swiftly use Hölder's inequality to get to the triangle inequality or Minkowski's inequality. But then I'm going to write down a full proof that doesn't rely on the duality because you're not supposed to know it yet. I just want to like put a teaser to, you know, repetition is the mother of learning, so it's good to see things many times. Okay, so argument by dual. Dual of a space is usually marked by putting a star there, and then if the dual of LP is LQ, if you know this, then for now this, okay, just listen, look at what I write here. So I'm interested in the norm of f plus g, right? In a P space, LP space. So there's no natural LQ here. So I mean, the only thing we have is the integral of f plus g modulus, the mu with a p there, and then an outside parenthesis and a 1 divided by p. So again, we would like to kind of split up this, but this to the power of p makes it very hard. Now, this is a norm, and the nice thing, so one idea with this duality is so the norm is a very complicated object. So we're gonna, so here's like the key formula of duality. So if I do the supremum of all functions h in LQ with norm being equal to 1, and then we do the integral f plus g times h, the mu. Okay, so here you see this is some ugly nonlinear object. Here everything I have is linear. I have an integral, f plus g is the object I'm interested in, and I added a new function h. So it's linear in h, is linear in the first. So it's like a scalar product. It's linear in the one variable separately, which is the f plus g, and it's linear in the second variable separately also. Of course, jointly, you have some sort of bilinearity. But the nice thing with duality is that, so I can do this integral for all sorts of h's, and but if you think about, you know, this geometric interpretation, so if this is my f plus g, and if I were to have like some scalar product here, then, you know, there's always, whatever h I take on the unit ball, there's some angle here, theta, between f plus g and h. And the scalar product is maximal when that angle is 0. So when h is equal to f plus g divided by that norm, right? So, you know, max of all h with norm of h equal to 1 in a Hilbert space of the scalar product of f plus g or whatever is here times h, that's equal to the norm of f plus g. This happens in all Hilbert spaces. So here, what I'm doing is I'm mimicking this formula. It's just that instead of taking elements h from the same space, I have to take them from a different space called the dual space. So if we accept this sort of lifting of this simple identity here we get from you know, vector spaces, Hilbert spaces if you want. Now, everything here becomes easy because the supremum is on the outside. Look how beautiful things become. This to the power of p disappeared. This 1 divided by p also disappeared. Everything which makes this the integral here or expression difficult disappeared in this expression. So of course I can put a modulus here, that doesn't change anything. And now I can, okay, we don't need a modulus, but now I can linearize here, right? So this is equal to the same supremum. I'm not writing out the same stuff one more time. But I get integral f times h plus integral g times h. So it's the same h for both of the integrals, and here's the supremum over all h's. Well, clearly, if I move the supremum, let that affect this one separately. Right? So now I disconnected the condition that h needs to be the same in both guys. So I have a supremum here of all h with norm 1, another supremum here of all h with norm 1. It gets bigger. But then this is equal to norm f by the same formula, by this duality, the whole idea of duality. And we get here that. So you see a beautiful way to achieve the triangle inequality. Having duality. But you can't have duality before you even prove that, LP is a Banach space or semi-Banach space. So how do we work out something similar without having this tool? Well, we just have to pick the right guy h. Instead of relying on this supremum here, we just have to pick a really smart choice of h that's going to do the similar trick here. So that's the idea. Now let's see the details. Okay, so I just wrote what I just said before. Here comes the clever choice. Pick h of t equals to f of t plus g of t to the power of p minus 1. Now, why would we do that? Well, first of all, is this even in LQ? It's not going to have norm 1, but that's okay. It's not so important. Up there it was important, but now we're not doing the supremum, so we don't care about what actually is the norm here. But let's check this. It is integral plus g to the power of p minus 1 to the power of q. And then we have a 1 divided by q, right? So now I get p times q minus q. Now you have to remember those formulas I told you to remember. That's actually equal to p. Yeah. Because I have that, I don't know where to write it, p plus q equals p times q. Right? So here I just get left with a p. So I have integral f plus g to the power of p, the mu. So I don't know what this number is, but I know that it's finite, right? So this is actually, at the end of the day, plus g norm. If I just had a 1 over p here, it would be the p norm. Now I don't have that. I have a 1 over q. So, I can turn this into a p, and then times the 1 over p, and then it becomes, you see that it's equal to this. Okay, so for now, at least it's a finite number. Woo! That's good. So let's see what we can get out of pairing them with f plus g like we did before. So now we consider, okay, I'm going to have to put a modulus here as well. Okay, what is this? To the power of nothing times f plus g to the power of p minus 1, the mu. So this is integral f plus g to the power of p, the mu. Okay, so now we get that guy. So we want some sort of inequality here, right? So we're going to repeat the same trick as before. So this guy up here is less than or equal to integral mod f. Now this modulus, now I can split it up. So I get mod f times h, the mu plus integral mod g, h, the mu. And this is the clever thing, right? Now we get linearity here in this. So I can split it up into two nice integrals. What's the first one? Well, of course, I also need to get something decent out of this computation. So I get, okay, so I'm going to keep the h here. I'm not going to introduce this f plus g to the p minus 1. Now, here we can use Hölder's inequality. Right. Now, this is equal to f plus g times the q norm of h, which we know that it's also somehow connected to the p norm of f plus g. So using that formula over there, I get the following. Okay, so the nice thing is now I have the right-hand side of the triangle inequality here, but then I have this annoying guy. But if you sum up, then also on the left-hand side of this inequality I've created, I have this guy, right? So if you forget about what's all that's written above, we just summarize what we have proved. We have this. And it looks like you will get one of these inequalities. You know, 1 is less than or equal to 1, because it's the kind of the same object appearing on both sides, but not. And here is something, again, I cannot explain everything with this. I told you there's some magical stuff going on with these p's and the q's. So this one has now got an exponent p divided by q, but here I just have a p. So if I divide both sides with this object, then I get right? And then you have to now remember the other of the magical PQ formulas. What's written here? Yeah, what the hell is written here? This is P. Oh, so we have 1 over P plus 1 over Q equals to 1. Okay, so if I do multiply everything with P and move to the other side, this gives me that 1 is equal to P minus P divided by Q. But this number is 1. Lecture is over. Thank you very much. Good night. Well, I should wrap this up. So, okay, we started out talking about yada yada. You know what I talked about. Doesn't matter. But we didn't really finish 3.3. So we have this Hölder, which replaces the Cauchy-Schwarz. We have the triangle inequality. What is left to be done? Well, we need to get this completeness business into the setting, right? That I started with when I did the norm spaces. We also have to deal with this fact that some integrals, some functions can be non-zero and yet the integral is 0. So we just have semi-normed stuff. And all of that, I leave it for the next class, which means today, for this class, you just have to read up until the end of proposition 3.3.3, Minkowski's inequality. And section 3.3 doesn't stop there, it keeps on going, but I will lecture on that next time. It's getting closer to, well, I mean, the corollary 3.3.4 here is by now pretty straightforward. It just says that LP, the curly LP, now I proved that the norm there is a semi-norm. So yeah, LP, curly LP is a vector space and the P norm is a semi-norm. Fair enough. But then they have an example and some yada yada that I will introduce next time. Okay, so don't read basically the last page of section 3.3. Well, read it if you want, but I'm going to talk about it next time. That is the end of the class. Thank you very much for listening and see you next time.